A function's basically a machine where you shove in a value and it shits out another. Inside this machine is a set of instructions on how to screw with the number you just put in. For example, it may multiply by 3 first and then add 6 to it. You'd write the function down like this, pronounced f of x, where the inputs are in the brackets. Or if you want to be super cool, you could write it down like this. If you want to know what you get if you input some number into the function, just replace all of these with that number. So if you shoved in 5, your output would be f of 5, which equals to 21. Note that the letter for the function doesn't have to be f. It can be G, H, or any other character. If we shoved in a bunch of numbers into this function and recorded their outputs, we'd find that each number gets its own unique output value. You can see it better by drawing a graph. The mapping of this function is said to be 1-to-1, because each input value is mapped to its own unique output value. For a function like this, the mapping is many to one, as there can be more than one input value mapped to the same output value. There are also something to many mappings like circles and stuff, but since functions can only have one output for each input, those are not considered functions. You can tell if a graph's a function or not by doing a vertical line test, where you scan a vertical line across the graph. If the line makes more than one intersection in the same input value, then it's not a function. Let's say that you want to take just a bit of this function, from here to here. Here's the graph of the new function. X can only be in between these two values. This is known as your domain, and it's the set of defined input values for a function. You can write it to the side of the function like this. If you wanted the entire function, then your domain would be the greatest possible domain of that function, which covers all valid input values. In this case, the function would be defined for all real values of x. We can write it like this, which means x is a member of real numbers. However, sometimes you won't be able to use certain values. The major things to watch out for are division by 0 and taking the even root of a negative number. For example, with this function, the denominator cannot be 0. After a bit of algebra, you'd find that x can be any real number except negative 3/2. The idea in writing this down is that you start with everything, all real numbers in this case, and then you take care of any exceptions. This function involves square rooting with variable x inside. So unless you want to venture into complex numbers, the root cannot be negative. You'll find that x can be any real number greater than or equal to 3/4. The range, or codomain, is the set of output values you get for a given domain. From the graph, we know that the output of g of x is in between these two values. If you wanted to get it algebraically, use the values given by the domain and find their corresponding y values. There are times where you need to be careful, for example with curves like these. The lower extreme of the range does not correspond to the lower extreme of the domain. Finding this one, however, is easy since it's the y-intersect. If it isn't, then you have to find the maximum or minimum point yourself. Another way to get the range is to rewrite the equation so that the input is the subject. That way, we can substitute in the domain to find the range. Composite functions are multiple functions stacked together, so the output of the first function is the input of the second function and so on. You'd notate it like this, pronounced f of g of x. Or you can write it like this. Order matters here. The input goes through the innermost function first. You can stack the same function together to make f of x or f of x, or more compactly, f squared of x or f cubed of x. The domains and ranges for these functions will be a bit more complicated, since restrictions in the domains will affect the input of the next function. If g of x also had restricted domains, you'd have to take that into consideration as well. You may have to combine restrictions, choose the stricter one, or whatever. As long as you keep note of them and you're working, you should be fine. Also, if you have multiple answers for the input value of the function, then be careful, because if that function has restricted domains, then you'll need to check whether your answers are within that domain. Inverse functions are functions that undo the action of the original function, almost as if you're moving back in time. If you have a function that multiplies by 3 and then adds by 6, then the inverse of that function will subtract by 6 and then divide by 3. The input and output will be swapped around, but the order of instructions remain the same. They're notated as f to the power of -1 of x. This does not equal the reciprocal of f of x, it's just retarded notation. The inverse of a function, when drawn on a graph, is a reflection in the line y equals x, since y and x, the input and the output, are being switched. For an inverse to exist, the function must be 1-to-1. The inverse of a many-to-one function will have a one-to-many mapping, and since a function cannot have this mapping, a many-to-one function does not have an inverse. To get the inverse of a function, first swap the inputs and outputs together. When you do this, the function is now inverted, so use f inverse instead of f. Then rearrange to make f inverse the subject. You could make this easier by substituting f inverse with y. When you invert a function, the inputs are now the outputs, and the outputs are now the inputs, so the domain and range also swaps. The domain of the original function is the range of the inverse, and the range of the original is the domain of the inverse. Some functions, like the reciprocal function, are self-inverse, meaning you end up with what you started with when you invert them. If you stack two of the same self-inverse function together, you'll also end up with what you started with. If we keep going, then notice how an even number of f's produce an x, while an odd number of f's produce 1 over x. Therefore, we can notate it like this, since an even number times any number equals an even number, and an even number plus an odd number equals an odd number. And if you for some reason need to know this, then this saves a fuck lot of time.